So we have seen that the infinitesimal time evolution operator is constructed this manner, satisfying the basic mathematical properties that we have extracted from physics. Unitarity requires that this is omega. We can proceed in two ways. Either first we try to identify the omega physically and then proceed to construct the finite form from this infinitesimal form, or vice versa. Let's finish with this mathematical feature, my mathematical property, that let's proceed to construct the finite form of it, and then, by the way, before that, let me try to find the equation satisfied by the U. Equation of U. And that equation is going to be relevant for construction of the Schrödinger equation. As I said, these two paths may be independent. I could have go ahead and integrate that infinitesimal form to get the finite form first, or vice versa. Doesn't matter. Let's see what is the equation satisfied by U. First of all, one thing to notice, perhaps you have already noticed, that this corresponds to a transition of this sort, right? The length of the interval is dt. Notice that this expression, this infinitesimal one, is independent of the endpoints, the initial point or its final point. It only depends on the interval. That's a very important property. It's independent of the endpoints. Good. So let me proceed to construct the equation satisfied by the U using the composition property, and I will use it in the following sense. Here, let me consider an initial time t0 and finitely separated time from it as t, and from that on, I proceed to make an infinitesimal one. I first go from t0 to t, and then make an infinitesimal one. Obviously, in this interval, I will be using the expression I have worked out. I don't know the finite form of it yet. Therefore, let me write the composition in relation that we have worked out before. Either I can go in straight from the initial to very final point, or go there in two steps. First from t0 to t, and then from t to t plus dt. How do I do that? I write it as, let me write the single step transition as t plus dt from t0 should be the product of, as I said, you reverse the order. You write this transition first, t plus dt t, and then u t0 to t. Just describing two steps and single step. Obviously, it is this expression which I have to write, taking advantage of the definition I have introduced. I emphasize that it's independent of the endpoints, whether it's t0 or t, doesn't matter. It's just the length of the time span of the transition which counts. Thank you for the warning. T0 to T, T to... Exactly, I was repeating myself. Going this way, and in the operator going the other way. Then what do I have? In the right-hand side, ut t0 minus omega dt, u t0. Okay. Let me move this to the left and write the left-hand side as t plus dt and t0 minus u of t t0. Right-hand side is minus dtu t t0. Notice that for the left-hand side, for both u entries, the initial points are the same, and the final points differ by this infinitesimal amount. So if I divide both sides by dt, and dt is in the right-hand side, cancel and take the limit dt going to 0, the left-hand side is nothing but the derivative, right? With respect to the first entry. So I write, to make it visible, I will write up here. The left-hand side then is du t t0 divided by t. And the right-hand side is minus omega, correct? U t0. So this is an equation involving sort of a differential equation satisfied by the u. Of course, these differential equations, to make sense, we have to give a boundary condition. The boundary condition is the t0 and t0. When the two entries are the same, you have the identity. So together with this boundary condition, we can integrate the first equation to get another equation, which will be integral equation. But now I am at a point which I need the physical identification of the omega to proceed with this equation further, or eventually to exponentiate or integrate this. Here I will use the correspondence principle, as we have done in the space translation case. We have borrowed certain information from the classical physics, in which commutators are replaced by the Poisson brackets, and in the formulation, Poisson formulation of the quantum classical physics, so similar, all those things, that is, symmetries and conservation laws, are even valid at the level of Poisson brackets. So physical meaning of omega, physical identification. Really, what I'm doing is an identification of omega. Classical physics, classical Hamiltonian, is the generator of time translations as well. Classical physics. Classical Hamiltonian is the generator of time translations. Then I go back here and try to make use, in order to make use of that information via correspondence principle. So I will use the correspondence principle saying that H should be related to the generator of time translations in quantum theory. In quantum mechanics. But first I have to really see the dimensions. Here, omega, from here, you see that it has the dimension of inverse time. I'm using dimensional analysis, put the brackets to indicate that it's the dimension, it's T inverse, right? Because the first term is dimensionless, and second is dimensionless. T has the time dimension, so the first one should have the inverse dimension. Inverse dimension of time is the frequency, right? And how do you go from here to eventually Hamiltonian? Einstein or de Broglie relations is telling you that energy and the frequencies are proportional. Einstein's version is E is h nu. Nu is the frequency, so it is 1 over the period. It has the inverse dimension. Therefore, if I have something like frequency, this omega is like a frequency, right? It should be energy divided by the h. Therefore, we identify, based on dimensional accounts, h divided by the h bar. That's the correspondence identification. Okay. So we can write the infinitesimal form of the u infinitesimal is I over h bar h dt. Well, that's a very sort of perhaps sketchy shorthand. I just wrote the interval because it's independent of the endpoints, right? So let's get the finite form of it using that. And also I can rewrite this equation. I rewrite it as h I'm sorry. Immediately, please repair it. This is an innocent typo, but eventually it may be very costly. We forgot the I in there, right? Put the I's back in here. So this is h over the h bar. Therefore, the right-hand side in here is minus I over h bar h u t t0. Okay. So we can now try to proceed, because that was an important achievement, although we have really used the correspondence principle, and it was in a derivation. It was carrying over information from classical to the quantum region, okay? So, how do I think of going from T0 T a finite transition? I subdivide it into equal segments of length dt, dt, dt. And the full finite transition is u tt0 is, I can go through these steps. How many? If there are n intervals, in here, then t minus t0 is n times dt, or you can solve for dt and write it as t minus t0 divided by the n. And all these u's, u infinitesimals, are the same. Independent of the endpoints, it is just the length. Therefore, how many? N many dt's. Let me write dt and I will replace n many. Write this as t minus t0 divided by n. And then let dt goes to 0 and take limit. We have seen this representation of the exponential before. Let me remind you, limit 1 minus plus the same, a over n going to infinity defines for you e to the minus plus a being an operator or matrix, right? So if I use that definition, remind you that definition, then this right-hand side becomes e to the minus I over h bar h t minus t0. Well, notice that here I have made an assumption. Perhaps I should have postponed this to a later stage, but anyway, I will make it more systematic. Here, what is the assumption? If h is time independent, it is so simple a case, I couldn't really wait for that systematic discussion. I will repeat it in the context of that systematic discussion. If h is time independent, this argument is true. Why? Because if the infinitesimal form of the h is that thing, but if h depends on time, it may be different at these individual intervals. I wouldn't be able to write this. If h is time independent, and as the other entity is also independent of the endpoints, then I could use this, saying that the same infinitesimal u for each transition. So this condition, this qualification, is a very important qualification. And in that case only, we get the time evolution operator in this very simple form. Now let me proceed with that, the equation that we have obtained in there. And let's see how do we make use or take advantage of that equation, whether it's good for anything. It's good for many things. First of all, it will give you an integral equation which can be iteratively solved to get the u explicitly for the most general cases. This is a very special case. That's the reason why I wanted to introduce that time-independent Hamiltonian situation. But Hamiltonians do not have to be time-independent. Most often than not, they are time-dependent. So can I talk about time evolutions? Of course I can. How do we do that? Let me turn my attention to this equation now. Notice that this equation is quite nice. If you move this factor to the left, it looks very much like the Schrödinger equation that you know from your past information. I haven't introduced the Schrödinger equation yet, but everyone knows what Schrödinger equation, right, is. So it is du tt0 dt h u tt0. And this indeed looks very much like, apart from this bilocality, or else it is the form that you are familiar, right? The Schrödinger equation, together with this. That's important. Now let me integrate this. Although the book says he postpones it to a later stage when he discusses time-dependent potential, I will do it in here. It's so simple, it would be a pity that I don't mention its general solution. Well, I will integrate this differential equation to convert it into an integral equation. I do the following. I change the t's to a generic t primes, and then integrate from t0 to t to be able to use this. So IH bar t0 to t dt prime du t prime t0 dt prime is the left-hand side. Right-hand side is dt prime h. In principle, it could be time dependent, so I'm not doing anything, keeping it in t0, integral from t0 to t. What is this? It is the integral of the derivative, the first entry being fixed. Therefore, it is what? It is the value of u at the upper point minus the lower point. So u t0 minus u t0 is the left-hand side. If I move now this I1 h bar here as minus I over h bar, here t0 to t dt prime h u t prime and t0. Okay, that's the right-hand side of the equation. Let me use the boundary condition, and that's the reason why I have chosen this particular interval of integral. So that is the no transition case identity. So I have the following equation: tt0 I over h bar t0 to t dt prime h u t prime t0. Okay, this is a solution. You say no. This is not a solution. This is an integral equation. Because u is the unknown that we are trying to construct. It appears in the left and it appears under the integrand in the right-hand side. There is nothing in here, so let's not get confused. So it's an integral equation. And these integral equations can be solved using the iteration techniques. They're easier to solve because iteration has a certain physical ingredient involved. You can, iteration, it goes as follows. At the zeroth order, there is no transition. The system is unaffected. You take that zero order solution and feed in the right-hand side to get the first order, because it involves h once. H is the agent causing the transition. No h, no transition. So it's really natural to call the zeroth order the identity. The leading term identity is the no transition case. No h, no transition, natural. So you take this first order, feed in the right-hand side, you get the second order because it's in a series involving no h, 1h, and 2h. You take the second order solution, feed in the right-hand side, you get a third order solution, which is a series involving no h, 1h, 2h, 3h. And in principle, you go all the way to infinity, and that's an exact solution. Eventually, perturbation theory, one can build on this, saying that if h is, here h, but we will do it for the interaction picture case, so that talking about h being small doesn't make sense. So this is an exact solution. So I can write the exact solution to this integral equation using the iteration method. Let me write down quickly those few terms that I have mentioned already without writing anything. So zeroth order, so iterative solution, iterative solution of the integral equation. By the way, this method is originally developed by Mr. Dyson in the context of quantum field theory. So we are carrying it over to the quantum mechanics. So zeroth order, meaning no transition. So U0 is the identity. No transition corresponds to no H. If no external agent, system stays there, right, on its own. So to get the first order, I take U1, which is I minus I over H bar dt prime H U0 T0 to T, right? I take the zeroth order, feed in the right-hand side to get the first order. What was the zeroth order? It's identity. So it is 1 minus I over h bar t0 to t dt prime h. I'm not moving it out. If it is time independent, I will move it out and reproduce that that other result. That because this was a direct construction from the exponentiation of the infinitesimal. Notice that I'm using the integral equation now to get the same result. But let me proceed in the general form, and let me put now the time dependencies to make it as general as possible, and then I will drop the time dependence to reproduce that result I have obtained. Okay. Let me not erase it. I will need to compare it now in a moment. So what is the second order? It will be sufficient, I guess. Second order will be U2 is I minus I over h bar t0 to t dt prime h, the first order, t prime to t0. I inserted the first order from the right to get the second order. I hope you understand the basic philosophy of this iteration method or recursive method, whichever terminology you like. Now let's substitute the previous solution to here. It is I minus, you have to be extremely careful now, time ordering comes in. I over h bar, t0 to t prime, so it is t prime, the limit, t0, dt double prime now, because I use a different variable, h t prime. Okay, that's it. Yes. So let me expand this. I minus I over h bar t0 to t dt prime ht prime plus minus, can you see this from the back? I will write it up, sorry. Perhaps it's not that visible here. I will write it here. Okay, here. So U2 is, the first term is the identity, of course. Second is minus I over h bar t0 to t dt prime h t prime, and then the minus I over h bar squared t0 to t dt prime, and t0 to t prime dt double prime h t prime h t double prime. That's the second order. So I write now the exact series as an infinite series, exact term. 1 plus n equals 1 to infinity minus I over h bar n dt prime to t, well, let me call dt1 to t, dt2 to t1, dtn to tn minus 1, lower limits are all t0s. H t1, h t2, h tn. Notice that if h is time dependent, if it depends on time explicitly, there is a time-ordered product of the h's. This order is important because this is to be integrated from t0 to tn minus 1, and the next one should be integrated from t0 to tn minus 2. This should be integrated from t0 to t1, and finally t1 is to be integrated t0 to t. Okay. So this is a general expression. Question. Perhaps before turning to question, we are finished with the most general cases. Now, obviously, we have to discuss different cases. Okay. Oh, by the way, I will set it aside yet and keep this general solution, U, the general. This was the second order. This is the exact general solution because this runs to the infinity. And there is no approximation or perturbation involved yet. That's the reason why it's an exact solution. Now, perhaps we are ready to talk about the Schrödinger equation, really. As I said, till now, we were acting as if we didn't know what Schrödinger equation is. What is the equation satisfied by an arbitrary state vector? Okay. Here's the equation satisfied by the time evolution operator. Now let me erase these generic things. That's the equation. If we take that equation, Schrödinger equation, and write it in the following form: IH bar du t t0 dt minus h u t t0 is equal to 0. Right, I can write it as such. And then if it is 0, its action on an arbitrary state chosen at time t0 also should be 0 because it's stronger. The stronger operator equality is converted into this equality. This is chosen to be arbitrary at t. 0. Then use the time evolution concept. That is this u, which is acted upon only by the first derivative on the first entry. So ut t0 acting on psi t0 gives you psi at t. There's only one time variable, so I will write it up. So the first left-hand side becomes IH bar d by dt psi of t, and move the second term to the right-hand side. Again, act on this by the u, convert it into psi t, h psi of t is equal to 0. This is the Schrödinger equation that we have been really waiting for. And this is the exact form of the general time evolution operator u, which enables you to construct any psi once an initial value of the psi is known. So that's a very good achievement. So we have to really, this is called the Dyson series, and we have to distinguish several cases in order to go. The general solution is there's no problem. You can, depending on the situation, you can use the general solution, but we have to distinguish several cases. Physics dictates us to do so. Okay, case 1. H is time independent. Now, how do I reduce that expression? If H is time independent, it is u t t0 is 1 minus I over h bar dt prime h. H is time independent, comes out t0 t plus dt prime plus minus I over h bar squared h squared dt prime to t dt double prime to t prime, etc. That is, this exact expression in the case h is time independent gives you this. Let's work it out. And the third one is dt prime t dt double prime dt triple prime, and all the integrals should be up to the limit of the other one. Well, this one is easy. t minus t prime, sort of mimicking that solution that we have directly constructed, the leading term at least. But what about this one? What is this? Well, this one is integral dt prime. I will write it here. That integral I will handle in here because I realize that you cannot see it in that corner. Let me call this the integral in time integral. And that's a notation. So this IT is integral t0 to t dt prime. Let me leave it there yet and carry out the t double prime integration. What is it? It is t prime minus t0, right? T prime minus t0. Okay. Well, there are several ways that you can proceed. You say, if you want, convert this t prime minus t0, say define it as tau, and dt prime is the same as tau, the limit changes only. So what is that limit then? D tau, and then when t prime is t, it is, tau is t minus t0, right? Yes, t minus t0, t0. So what is this? 1/2 tau squared t minus t0 minus t0. Correct? D tau. We are not dropping anything, I guess. T prime minus t0. You're right. Thank you. Because if it is t prime minus t0 is tau, then if I let t0, the lower limit is 0. Fine. So it's finished. So you see how it's going. Claim. The first line is single integral t minus t0. The second one, 1/2 t minus t0 squared. Do it one more. You do 3 time order integral, then it's going to be 1/3 factorial t minus t0 cube through change. So then the series goes like 1 minus I over h bar h t minus t0 plus 1/2 factorial minus I over h bar squared h0 squared t minus t0 squared, which you resum now, minus I over h bar h t minus t0. It's exactly the same expression as we have obtained by direct construction. If h was time independent, we had subdivided the entire finite interval into equal segments of length dt, and there are n of them because h doesn't depend on the interval and nothing depends on the endpoints. So we exponentiated to get that result, and this is via the exact expression, this one. So it's nice to see that the same result holds, is obtained via 2 different methods. So this is the case 1, when h is time independent. Let's define considering the case 2. It's case 2, okay. It's a strange thing. Sometimes physics really have these strange cases. I will illustrate. H is time dependent, but H at different times commute. Well, this is a time, this is a spin 1/2. I will illustrate. We are going to go through those examples in detail, spin in an external magnetic field whose direction is the same, but its strength is changing. So you have a special set of magnets so that strength is increasing or decreasing. Well, in that case, example, B is OZ, but BT. But strength changes. Its direction is fixed. Well, that's much better. Direction is fixed. Fixed. But strength changes. What is the Hamiltonian for an example of that sort? Spin in an external magnetic field is minus B. So what is it? Minus Q. Well, if it is an electron, then plus E G divided by 2mc S dot B. G is 2 for the electron, so E divided by mc. And this, if it is fixed in direction, we can choose it to be the third direction, B SC. But if its strength is changing, so it is the Hamiltonian, interaction Hamiltonian for a configuration becomes this. Obviously, Hamiltonian will commute because the only operator is the SC, and in each term there will be time dependencies coming from here. If I write it as omega t, for instance, there will be the time dependence, but operator is the S, Z component of the S, it commutes with each other, and that condition is satisfied. If that condition is satisfied, then how do we proceed? We proceed in the following manner. We go back to this expression, bring the H in, and each term keep the H's in, but we will use the advantage that H is at different times. HT prime and HT double prime will commute. So there will be no time ordering, and result will come out to be the following. U, T, T0. This exponentiation, summation is the achievement. Remember this exact expression we couldn't sum apart. Well, we could do in field theory when we introduced time-ordered products, but we don't want to do such sophisticated things in such a simple class. So time ordering, without introducing time ordering, we couldn't exponentiate and sum it, turn it into such a simple form. But notice that it's a very simple form, exponentiated, thanks to the fact that Hamiltonian happens to be such that at different times it commutes. They commute with each other, despite the fact that they carry time dependence. So I keep this under. Although I'm not going to discuss these kind of things in here, there are those geometrical Berry phases, adiabatic theorems, and these kind of arguments are relevant for those cases. As I said, I'm not planning to include those beautiful subjects in this class. We have to proceed as fast as possible. I think that's a good point to give a second break, and we will continue after that.